Hello and welcome to part 3 of our revision of radiation. In our previous lessons we have looked at the basics of radiation. We've then looked at energy levels, photons, absorption and emission put together in case you couldn't tell. And today we are looking at the uses of radiation, fission and fusion. So I'm hoping that's covered most of our radioactivity topic. Obviously there will be small details that have been missed, but I'm hoping that it's reminded you and you've got a bit more of a grip on what you should know. So I've really summarised the uses of radiation and I've just given you a couple. So alpha is used in smoke detectors because it's very, very ionising. Radioactive americium, and you're not expected to know which particular element goes into it, but just so you know how it actually works, releases alpha radiation, which ionises the air inside the detector. Smoke from a fire absorbs alpha radiation, altering the ionisation and triggering the alarm. Now, I should say that although it's very useful for you to know one example of a use of alpha, beta and gamma, you may also be given a completely random use which you've never seen before and asked to explain it. So in terms of that, just start thinking, is it ionising? Is it going to be blocked? What's it blocked by? And apply your knowledge to it. So these are good to know, but you may be given something random in an exam. So beta radiation is used for monitoring the thickness of materials such as paper, plastic and aluminium. The thicker the material, the more radiation is absorbed and the less radiation reaches the detector. It then sends signals, that's a detector, apologies, to the equipment that adjusts the thickness of the material. So you have a beta source on one side, then you've got material in the way and the detector on the other side. And if there's too much material, if the material is too thick, then the detector will not detect much beta, and so it will send a message to the computer to say, right, start thinning it out again. It knows what level it should be. Gamma radiation is used in the treatment of cancer, testing equipment and sterilising medical instruments. We also know that it's used in gamma cameras, gamma knives, etc. There you go, there's some uses. Let's go on to nuclear fission. And what is a physicist's favourite Friday night takeaway? Fish and chips. Ba-dum-tsh. Oh yes, it's a classic. Right, nuclear fission. You take a large nucleus and you split it up, basically. In order to do this, so fission can actually happen, in fact I'm going to write on here. So one large nucleus, there you go, that's my nucleus made up of protons and neutrons. I know you can't see them, I've just drawn a blob, but hey ho. And you split it up into two smaller nuclei. Now this can happen spontaneously, however, you can't predict, spontaneous obviously, you can't predict when that's going to happen. So in order to ensure that fission happens, you generally get a neutron to be absorbed into the large nucleus. So you have a neutron being absorbed into the large nucleus and that causes it to become more unstable and break up. So if you look at this yellow box here, you've got uranium-235, should say nuclear fission uses very, very large nuclei. So that's why you've got 235 as that mass number of uranium, showing just how big it is. Plus a neutron, which is absorbed, goes to a smaller nucleus, smaller nuclei, neutrons and energy. So this type of energy release is used in nuclear power plants, so all up and down the country. And we tend to use uranium or plutonium because, as I say, they're very heavy nuclei. The energy is then used to heat water to form steam, which turns the turbine, connected to a generator that generates electricity. So here you go. Hopefully you vaguely remember this from P8 as well. There's quite a lot of crossover with power plants. You've got that nuclear reactor. Apologies, this animation won't work on an iPad. You've got that nuclear reactor here, which is giving off energy from nuclear fission, which boils the water, turns it into steam. The steam turns the turbine turns the generator, electricity is made, lovely jubbly. So that's nuclear fission, one large nucleus splitting up, making smaller nuclei and giving off energy. Now you will notice, as well as the neutron that goes in, it also gives off neutrons, and it tends to give off 2 or 3 neutrons. So those 2 or 3 neutrons then go off to find their own uranium nuclei to split up, which can cause a chain reaction. So here you've got that neutron going into uranium-235, making it unstable, It then splits up. You can see here, these are the products of its split. You've got two smaller nuclei there, krypton and barium. You're not expected to know which elements are created, just that it's smaller. And you've got those three neutrons, each of which are going into another uranium-235, which splits up and again gives off 3 neutrons. So with 1 neutron at the beginning, you can see we've actually ended up with 9 neutrons being released on the right-hand side. So if this was to carry on unimpeded, it would be very, very dangerous. You'd have a very quick release of energy, which is really quite uncontrollable. So what they tend to do is they have certain control methods to stop this from happening. So every time a neutron goes into uranium, yes, it releases 2 or 3 neutrons, but then they have something called a control rod, which absorbs those excess neutrons, so they never go on to make another chain reaction. So for each neutron that goes in, you only really get 1 neutron out, so that it stops it going on and getting a bit out of control. So here we go. In a nuclear power station, control rods made of boron absorb excess neutrons to prevent chain reactions getting out of control. In a nuclear bomb, there is no control method, and so a huge amount of energy is released very quickly. Now, on the right-hand side here, you can see a diagram of a nuclear reactor. You've got these yellow fuel rods, which are in the reactor. Fabulous, they're all surrounded by water. So reactions are happening left, right and centre, but then you've got these black control rods, and you can see they hang down from the ceiling. Now you can change how much they're actually in the nuclear reactor. So if you have them lower into the nuclear reactor, there'll be more control rod in there, they'll absorb more neutrons, and so they'll slow the reaction down. But if you remove them by lifting them up, less control rod, absorb less neutrons, you can speed the reaction up. That's basically it. That's nuclear fission. Right, nuclear fusion. Take 2 small nuclei, smush them together, technical term there, probably should say fuse, and create energy. So, there you go. Small nuclei join together to form larger nuclei and energy is released. In the sun's core, hydrogen nuclei fuse to form helium. Small nuclei can fuse to create elements all the way up to iron, the most stable element. And again, you'll see that links in with our P8 when you look at the life cycle of stars and fusion happening in main sequence and red giant stars. So this only happens under certain conditions, and those conditions are the same as this delicious cheese toasty. It only happens at very high pressure and very high temperature. And the reason that you need high pressure and high temperature is because you are trying to take 2 positive nuclei, which are going to repel each other, and force them together. There is progress being made. So this is pretty good. In fact, I should probably change this PowerPoint. There is progress being made in nuclear fusion reactors. It's just that so far they're not massively energy efficient because of the amount of energy you need to put in order to create the high pressures and high temperatures. And that's it. Right, lovely jubbly. See you soon.